values of the function in the same way that you can, I mean not in the same way, but you can, just like we would put in numbers in here to figure out, what is, when x is 1, what do you get, right? You can tell me. When x is 2, what do you get? You can tell me, right? You can do kind of similar thing here. So this also basically defines the function, right? Okay? So this defines our function. And then we ask, what is the limit? Okay, so how do you read this again? First of all, how do you read this part? X approaches 9, and then how do you read the whole thing? The limit of f of x as x approaches 9. Okay, you're all about a year ahead of me when I did this. I never got that straight. Okay, but anyway, and that makes things really difficult. The professor or teacher is saying all of that and it's not registering in your brain. It doesn't work very well. Okay, anyway, what is this? So this is the limit as x approaches 9. So in this case, it's not undefined at a, right? Or it's not undefined at 9, right? So there's really no issue here. It's kind of like, again, it's overkill, right? The actual value, the actual height of the graph at 9 is the same thing as the limit at 9. Okay? So what is the answer? Negative 18, right? Okay, and how about at negative 9? So that means over here. So then what is it? Negative 9, right? Okay, does everyone get that? Okay, how about here? It's the same thing. Now, okay, so this is the same thing, so we don't need to do that. But let me ask you, sorry, we haven't done this yet, but if I wrote this, you can probably guess what I mean by it. So let's use that function, which they call f. So if I wrote this, so you can probably guess what I mean by that. But anyway, before you guess what I mean by that, let's read it. How do you read this? X approaches infinity, or x approaches positive infinity, either way. So how do you read the whole thing? The limit of f as x approaches positive infinity, right? So what do you think that means? Because usually we have down here just a number, right? But I didn't put a number there, I put that sideways 8 symbol, right? So, but what do you think that means? That was that question that I started out with today. I said, what happens to the function as you get larger and larger x's? Right? So that's what we're asking here. Or, I'm sorry, that's what I'm asking there about this function. So what do you think happens? What is this arrow supposed to suggest? Just going higher and higher, right? So this arrow is supposed to suggest that as we move in this direction, it just gets bigger and bigger. So then we would write and if that had been the question here, which it's not the question here, but if I had put infinity here, then you should put infinity here as well, right? So we would say the limit as x goes to infinity is infinity. Okay, and what about this one? If we said as x goes to negative infinity, what is this suggesting? The answer is negative infinity. Okay, so we will have those questions also. But not yet. Oh, here. Okay, so this one is better, is different. So this says what? The limit as x goes to negative infinity of this, right? Okay? Now here's the picture though. So what's going to be the right answer for this one? Yeah, we're asking what happens to the height. This is different than this, right? This one arrow is suggesting what? That it just keeps decreasing, to negative infinity. But this picture is suggesting a different thing. What? That it's getting closer and closer to the x-axis, which means that the height is getting closer and closer to 0. Okay, so we would put 0 in for this one. Okay, is that clear? Okay, so the point here is to learn this tool called the limit, because we need it after we master it for finding derivatives, or like slopes of curves, so to speak. Okay, but anyway, we need to master this, but we're just about finished with it. Okay, how about this one? Okay, this is what is this, what's the height, okay, first of all, what's the height at 0? When x equals 0, what's the height? So there's a circle here and a dot here. So the height is what? I guess a is equal to 3, so the height is 6, right? Okay? It's not negative 3, right? Okay, does everyone agree? Well, another question we could ask is this actually a function? If you use the vertical line test, does it work? And it does, right? It is a function. Okay, if you draw a vertical line anywhere, including here, you only cut it in one place. Okay, so it is a function. So what questions should I ask? Okay, as x gets closer to 6, so that's here. So what's the limit? Means what is the height approaching? If you played that game, what would you guess? So 0, right? You're giving it closer and closer to 0 on this side, closer and closer to 0 on this side, you would guess 0. Right? So the answer is 0. How about, okay, now here's a new symbol, which I have to explain. And that is a bad symbol. I mean, that's a bad example. This is a very bad example for me to introduce it. So I won't use that example to introduce that simple symbol, because it's really misleading. But let's use this one. I use basically the same one, but just like this. Like that. It's basically the same picture. Just shifted over and changed a little bit. Okay, now, so let's say this is 1. So just to review, we just did this basically, but this is called f. So if I said that what's the limit as x approaches 1 of f, what is that answer? So as we get closer and closer to 1, what would you guess? 0. Okay, we just did something like that, right? Okay, now, however, if I did this, okay, now there's a kind of conundrum, right? Kind of confusing, right? Because, well, but what is the answer? There is no limit, right? Because if you guess from this side, you're going to guess what? 3. But if you guess from this side, you're going to guess what? -2, right? Right? So you get you're going to guess 2 different numbers, right? In that case, we said there's no answer. Right? So we have to write. Okay? Does everyone follow that? You follow that? Okay, so if we ask that question, the answer is doesn't exist, because there's no single number that we would guess. Okay, however, now we introduce a new notation, which is that. That does not mean plus. That does not mean positive numbers. Okay, it doesn't mean positive numbers, but, okay. So what it means is only looking from the right-hand side of 2. So you don't have to look from the left-hand side of 2. In fact, you don't look from the left-hand side of 2. Okay, then do you have a single number which you would guess? Yeah, you would guess 3. Okay, so that's what that means. So that means only looking at values to the right of 2. Okay, so that's what that means. And then what about this? What's that one? That means only looking at values to the left of 2. So what would you guess in that case? Negative 2. Okay? So this has a name. It's called the right-handed limit. Okay, because it's only things to the right of 2. And this has a name. It's called the left-handed limit. And that's because it's only things to the left of 2. Okay? All right? And then there's a theorem which says that suppose this is true. Suppose that's true. So what does this say? If you just look from the right of A, you get a limit of C. And if you just look from the left of A, then you get C. Then the theorem says that these two together imply this. Imply what? If you come from the left-hand side and you get C, and you come from the right-hand side and you get C, then this is called the general limit. This is called the left-handed limit, right-handed limit, left-handed limit. So if the left-handed limit equals the same thing as the right-handed limit, then the general limit will also be that. Will also exist and be that. And it also works this way. Is if the general limit is equal to C, then the left-handed limit and the right-handed limit will also be C. And those have to be proved, but we don't have we're not going into the so-called epsilon delta proof. So the epsilon delta is the real definition of limit. We sort of gave a kind of my game definition. Okay, which is like an intuitive definition, but doesn't allow you to actually prove that the limit is blah 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 for a particular function. Okay, so you need a more mathematical version of it, and it's usually called the epsilon delta, and that's what we would do if we had a full-blown calculus class. We'd have to do that, but I really hate doing that actually. It's confusing. But you can look it up, and it was developed by someone named Karl Weierstrass in the 1800s. Kind of gave this very precise meaning to limits. So maybe before that it wasn't so precise actually. But anyway, but we're not going to do that. But anyway, what I'm saying is that to actually prove these two theorems, you need to have that. Okay, you need to go into the definition. But it seems obvious, right? It seems obviously true, right? That if the whole limit, the general limit is equal to C, then the left hand has to be C and the right hand has to be C, and vice versa, right? It seems obvious. But just because something seems obvious doesn't mean that it's true. That's why we have to actually prove it. Right? A lot of things might seem obvious, but they're not true. For example, one of my favorite examples is, how many people probably know, but people aren't aware of this. How many people have studied physics? A little bit. But how many people have studied what they call special relativity, which is like a portion of relativity? Maybe not. So let me just ask you a question. Suppose this is just completely different, but just for fun. Suppose you're in a train, right? And you're here, and your friend is here, and you take a ball, and you throw it to your friend, and let's suppose you just throw it at 50 mph forward. Okay? So obviously, your friend, the ball gets to your friend. Basically, it's going the same. Let's suppose there's no friction. So it arrives at your friend at the same speed, right? Okay. Now, suppose the train is moving, though, like this, and it's moving at it's moving at say 60 mph, right? So suppose somebody else, the third person, is standing on the ground, right? So they see the train moving at 60 miles an hour, right? Ahead, right? So, so even if this guy doesn't even throw the ball, if he just holds it, this guy will see the ball is moving 60 miles or in this direction, right? And then if the guy throws it at 50, then he will see the ball moving at what speed? 50 plus 60, right? This person, right? 110, right? That's natural, right? That's normal, right? Okay? However, for some bizarre reason, instead of if it's a ball, instead suppose he has a flashlight, and he shines it forward, right? So it takes time for the light to go from here to here, right? That's supposedly true. I don't know how they know that. I mean, it's not intuitively true, right? It's not part of our natural experience, and it's not necessarily intuitively true, but apparently it is true. Okay? So it takes time for it to go here. So that means it's moving at some speed, right? Which is called the speed of light. Right? That's what the speed of light means. How fast it's moving. So that's usually denoted with a C. I don't know why, but it's just denoted with a C. So C means the speed of light. So that's how fast it's moving, right? Okay, now suppose that this guy is standing here and the train is also moving. So, I'm sorry. So when this person gets the, he will say that, it took a certain amount of time for the light to reach him, and therefore the speed was blah, blah, blah. Therefore the speed was C. Right? Okay. Now here's a person on the ground, and let's suppose that the train is not moving at 60. Let's make it faster. Let's make it like 0.9 C. So almost the full speed of light, but not quite. Okay, so the train is moving super fast. Okay. Now the question is, how fast is he going to measure the speed of the flashlight going? So if we did it the way we just did it before, we would say what? C plus 0.9 C. Right? Just like we said 50 plus 60. Right? So you'd say C plus 0.9 C, right? In other words, you'd say 1.9 C, right? So that's what he would, fast light would be moving, right? But according to the way people do physics, that's not the answer. The answer is C, which obviously is not intuitive at all. Right? Right? It doesn't make any sense, right? But that's what physics says. I'm not sure I even believe it. But that's basic physics that every physicist will tell you is true. Nobody will deny that except for me. Yeah.
Does
Yeah, wait, hold on, let me finish the story. So, the phrase they use is, the speed of light is constant in every frame of reference. So this is one frame of reference when you're sitting in the train, and a different frame of reference is when you're sitting here. The speed of light is always the same, no matter what frame of reference you're in. So, for this person,
still C.
For this person, it's still C. Maybe I'm the only person who doesn't believe that. Because as my physics professor said to me a long time ago, he said, physics is actually like a religion. So you have to believe what do they call it, like the catechism, or you have to believe the rules. You have to accept them kind of on faith. I don't know, he was a radical guy. But anyway, it seems pretty bizarre, and I'm not sure if it makes sense. But they supposedly they've measured these things. It seems pretty hard to measure those things. But there are some so-called experiments that supposedly measure this and show that it is true, but I still have my doubts. But anyway, that's what that says. The speed of light is constant in every frame of reference, and that's completely given in physics. You ask any physicist, they're all going to tell you that. They're all believers. Okay, I don't know about that. But so anyway, the thing is that not everything that's intuitive is necessarily true. At least it doesn't, according to physics, it's not true. Right? Because intuitively we would never say that. Right?